Today we make every atom count, and if you want to know what that means, then stay tuned for today's video as we are looking into Silicon Quantum Computing, a company that makes quantum computers. So if you want to know more about them, stay tuned for today's video and let's start right away. So here we are on the website, and as I mentioned already before, every atom counts, and that's trademarked. So unrivaled quality, atomic scale manufacturing, and phosphorus atoms precision placed in pure silicon combined to make the world's highest quality quantum computing platform element 1415 qubits. Let's quickly go through the website and then I talk a little bit about that as well. What do we see here? So we see a couple of lab measurements, then we see some vacuum chambers and instruments. So a nice little video clip of probably how stuff is being produced. So elegant simplicity, our quantum processors only contain two types of atoms, silicon and phosphorus. This simplicity allows us to realize the highest fidelity algorithms of any platform. And I mean, probably also even more precise, as in not only just silicon atoms, but only just some very specific silicon atoms and not certain other ones. But I guess we will learn more about that in a couple of moments from here, because I think they only use a specific isotope of silicon. So total integration, fully integrated in-house chip manufacturing enables SQC to develop tools, processes, and integrated processors in parallel and at speed. We design fast, we learn fast, we deliver. And then we see one of those chips over here with some radio frequency lines attached around it. Then we see here, so SCQ delivers both analog and error-corrected processors. Products available now. So there's the QML simulation, Watermelon and Quantum Twins, a quantum feature generator for machine learning, and a quantum analog simulator for chemicals and materials design. And then product available soon is Jalapeno-one, a gate-based processor for experimentation and advancement. And then there's a link to the products here. So a quantum feature generator for machine learning. Okay, then we have this quantum analog simulator as well. And then down there we have the gate-based. So that's actually the one that is going to be interesting for the quantum computers, right? The gate-based chip, which is going to be available soon. And then on this other side here, I think we see something of how this actually works in the details. So we see there's some silicon substrate down here. Then I guess over here, I don't know, it looks a little bit like graphene layers to me, but I don't think there's going to be graphene in there. Maybe we will see something about that later, because these ribbon kind of structures look a little bit like a scanning tunneling microscope image of graphene or graphite stack. Then I guess in here we see all the phosphorus atoms, I would assume. Then we see here these electrodes that are being used to control and measure them. There's epitaxial silicon on top, and then there is some native oxide layer on top to kind of cap the wafer. And usually this is of course not like separated from each other, but they are all stacked together into one chip. As like when you scroll down, you can see up there in the edge. Now, become entangled with us. SQC is a leader in the global race to manufacture the highest quality qubits and most useful quantum processors. Our future plans are ambitious, and so are we. Join us. And then there's a link to the open positions. Something else about the company. So established team, founded in 2017 and building on 25 plus years of world-leading technological excellence and delivery. 25 plus years of sustained delivery, 280 million US dollars existing investment, 200 plus total patents, 250 plus refereed journal publications, in 2033 commercial scale error corrected quantum computers, 70 plus technical personnel alongside 20 commercial staff, 2 products in the market driving quantum advantage, the one that we saw before, and 1 week chip manufacturing cycles. Then down here we see the news article. I'm recording this in March of 2026. And indeed, we see some latest news article here from March 24th in 2026, which says NRFC investment accelerates SQC's atomic scale manufacturing. Then down here, we see some way to get in touch or to stay in touch with them by entering your email for a newsletter. And then again, the slogan, every atom counts, and the typical links down here. Now let's quickly scroll up again and take a look into the products first. So what products do we have? We saw that there are, I think, 2 chips, but now we also look at the products. So size quantum advantage, cloud and on-premise flexible deployments to suit your organization's requirements, AI acceleration, boost classical machine learning performance by incorporating quantum features, and then custom hardware specialized for materials discovery and chemistry. That is the system. Then we see again the chip here, so quantum machine learning. Our quantum feature generator for machine learning exploits the power of quantum mechanics to identify hidden insights and value in your data. By combining classical and quantum processors, we enhance the accuracy of machine learning models, particularly for time series data and sparse data sets. Take advantage of the power of QML today, quantum machine learning, right? Watermelon, SQC's quantum machine learning processor, is currently available to purchase and via cloud access. Learning processor, schematic of our quantum enhanced machine learning processor, Watermelon, that allows us to use quantum reservoir computing for a variety of machine learning applications, finance, defense, transport, communications, energy, and pharmaceutical. To be honest, I have no clue what this idea of quantum reservoir computing is. I guess it is using so usually the coin term of the reservoir comes from something like thermodynamics or from the thermodynamics field, which is usually statistical physics, but then probably at the quantum limit. So statistical physics in the normal limit is that room temperature where everything is like smeared out and you don't really see much of the quantum nature because everything is completely distributed via all different energy levels. Whereas if you cool things down, if you're running at the quantum limit, you can also see some quantum distribution effects. So maybe that is making use of that. But to be honest, I don't really know. Then we see here the quantum twins, windows onto commercial scale quantum chemistry. So at SQC, we manufacture on atomic scale. This exquisite precision enables us to create custom chips that physically encode direct analogs to our desired quantum system, enabling customers to understand what is beyond classic computation. Excited? You should be. Our commercial and product teams work directly with you to understand the specific structures that you want to explore and optimize, to tune and scale our representations of your complex systems to deliver insights and answer untenable on any other platform. Quantum twins, our analog quantum processors, are available via a direct contract with SQC. Now let's quickly take a step back, and I'm just gonna make a couple of assumptions about the technology without seeing if these things are true, because I haven't seen too much about this yet. But let's quickly talk about this idea of phosphorus atoms and silicon. So I think previously in the series we've already talked about spin qubits. So qubits that are confining single electrons within a two-dimensional electron gas, for example, or within a silicon wafer. So you think of silicon as this crystal, and then you have the electrons that are moving around in this crystal. That's what a semiconductor more or less is or how it works. And now you are basically able to confine a single one of them, and you cool the system to a very low temperature so that this electron is not affected by the crystal too much anymore, because otherwise the crystal is vibrating and shaking the electron back and forth, and then it's not really stably interacting as a single quantum system. But if you can, let's say, use low temperature, freeze out all the other electrons and all the movement of the crystal, then you have the single electron sitting there, you flip it back and forth, and then you do some operations with it. Now, if this is kind of complicated because you need a lot of electronic control, you need gates on top which can push out all the other electrons and make sure that your electron is sitting in a defined area. You need other gates that are then controlling those electrons, moving them back and forth. So it's quite complex. And it requires also a lot of simulation to understand what is actually going on depending on the gate designs. So the designs of the electronic environment that you are setting with those electrical pulses. A little bit of an easier way in terms of control might be if you just had one atom within your silicon crystal that is sitting at a specific location that has this electron attached to it, and that's the idea of phosphorus. So phosphorus is considered a donor in that case, so because it donates an electron, and this electron or this atom, this phosphorus atom, can then be controlled again using these electrical pulses. And the good thing is you don't need to push any other electrons out or anything because you have it sitting right where the phosphorus atom is. For that, you need to be able, though, to put a single phosphorus atom into your quantum or into your silicon wafer, which otherwise is completely just silicon. This is something which is not so easy to achieve. This requires a lot of precision, especially if you want to place this in a very specific location. Now, traditionally, the way of how donation is done, for example in diodes or in transistors that we are using for today's chips, is you basically put some stuff on the wafer, then you heat it up, the stuff is diffusing into your wafer, and thereby you basically create this doped areas. And there's N and P doped, and with that you build diodes, you build transistors, and so on. But these are many atoms, so it is basically big clouds of atoms that kind of diffuse into your silicon. Doing it with a single atom is much more complicated. You cannot just put it on your wafer, heat it up, and wait that it diffuses inside. Oftentimes what is done is you have something like an ionizer, a gun that is basically ripping off one electron from the phosphorus so that it becomes electrically charged. Then you use electromagnetic waves or electromagnetic pulses, like in a railway gun more or less, to accelerate this ion, and then you shoot it into the silicon wafer. And there are specific functions that can tell you like how deep this electron or how deep this ion will actually go into your wafer before it gets stuck, depending on how you twist the wafer, because it's a crystal, right? So if it's in a specific angle, you just shoot through. So you have to twist it a little bit maybe, and then you use different types of materials with different crystal structures, and then it gets stuck somewhere. And this is called ion implantation. It's a process that actually exists, but doing that with single ions at a precision where you exactly know where they would land is quite a complex process. And my guess would be that this is something that this company has optimized in terms of a process. Now, this is without knowing how they do it exactly, right? But that would be my guess, how they put the phosphorus atoms inside. And that's also how they exactly position them in certain places. And if you do this, so if you can position them in certain places, you can put them in all kinds of geometrical shapes. And by that, you can simulate basically the configuration of, for example, specific molecules. Because molecules, they are also just more or less defined by the way that their electron shells or the electrons are behaving. So chemistry is mainly happening on the electronic level, right? You don't have the nuclei of the atoms interacting with each other. That would be fission or fusion. But chemistry mainly happens in the electronic shells, so it's an electronic topic. And if you can now I don't know, implant these phosphorus atoms in specific positions. You can kind of mimic specific configurations, and that might be interesting to kind of, on an analog way, simulate or emulate specific quantum molecules. That is all basically just me guessing here. As I said, I don't know too much about how this is done precisely. Maybe we will figure out soon, but that would be my guess of what is happening here and why this could be interesting. And by the way, similar things, no, not similar things, but other things have been done where people were taking atoms and using microscopic tips to move these atoms on a surface. So with scanning electron microscopes, for example. And there was also some Nobel Prize awarded to that by Binning and Rohrer at IBM Labs, I think. And they were taking these atoms and putting them in specific locations on this surface. And then you could actually measure their wave function more or less. And you could really see the waves that these configurations are producing and how they are, let's say, behaving in a quantum mechanical way. For example, if you put them in a circle, you will see that there's some interference pattern with some peak in the center of that circle. I think that was even used as an image for some textbook. And yeah, there were a lot of very interesting experiments done back then, because you can see more or less the quantum nature, right? Okay, but let's move on here on the website of single quantum computing. So there's Jalapeno 1. A unique advantage of SQC's 14-15 qubits is our extremely high fidelity algorithmic performance. With long T1 times, we observe minimal bit flip errors. We achieve break-even logical performance with just 3 physical qubits, paving the way for efficient and effective error correction. I think these long coherence times can be achieved because if you, for example, use only one isotope, I think it's silicon-28 isotope, that one comes without any nuclear net spin. So if you're looking at the nucleus of your atom, you have protons and neutrons, right? And they all have their kind of spin properties. And if you have an uneven number, that means your nucleus ends up with a net of one, let's say, magnetic property, right? With a net magnetic property. That's, for example, what can be observed in gallium arsenide if you're looking into those systems, because basically, yeah, you have this odd nuclear behavior. Now for silicon-28, I think it's 28, you don't have that, and you can actually create silicon-28 layers on top of a silicon wafer. So you buy a normal silicon wafer as they are being used at TSMC, for example, today. Then you use what is called a molecular beam epitaxy process, where you epitaxially grow a silicon-28, purified silicon-28 layer on top. And on that layer, you are basically, if you're implanting your phosphorus atoms there, they don't feel too much of the silicon around them, so they really behave like single atoms in the vacuum, more or less, but they're actually embedded into a chip, which makes it kind of easier to process them and easier to access them, maybe also electrically. Okay, so then stay updated on discovery. Okay, that's the email part that we've seen before. So that's about the products. Then here the 14-15 qubits. I think that's probably the interesting one, right, with the chip. So the SQC Edge, we are the only company in the world to manufacture at atomic scale. We precision place phosphorus atoms in pure silicon to make the highest quality quantum computing platform, 14-15 qubits. Okay, here we see then a couple of the precision benchmarks. So world-leading performance quantum computing processors made with atom qubits in silicon have demonstrated exceptional performance combined with our rapid manufacturing capability. This provides the best and most cost-efficient platform to deliver quantum computing on a commercial scale. We see here 0.13 nanometers, the world's most precise manufacturing, 8 nanoseconds gate operation speed at deliver answers fast, then 99.9% single qubit fidelity, gate fidelities, 99.95% 2-qubit gate fidelities, and then we see 30 seconds long coherence times enabling deep computation, and then 99.5% Bell state fidelities, the highest quality entanglement. And again, talking about the race of different technologies, right? We always want to look at how long is the coherence time of your qubit. So here this is 30 seconds. And how quick can I actually change the qubit state? Because it doesn't help me if I can keep the qubit for seconds in a specific state, but I need minutes to manipulate it, right? Because then basically it will still decohere until I can actually do the manipulation. But here we see that it's 0.8 nanoseconds that you only need to kind of do some gate operations. And on the other side, you have 30 seconds of coherence. So very long and stable coherence. So you can probably perform very deep quantum algorithms, deep circuits on that, because the coherence is that long. So if you keep your program running for 30 seconds, you can do a lot of operations if every operation only takes you 0.8 nanoseconds, right? That's kind of the idea. So you can build quite powerful programs with that. The other thing that usually is also very important is how the connectivity looks. So how many qubits can I actually connect to each other? Can I create a superposition across all of them? An entanglement across all of them? Because it only really becomes powerful if I can entangle them very, very well with each other and then create superpositions, right? And I think there's not too much mentioned on this here in the details. So the secret to our success combined with our manufacturing capabilities is awesome. Simplicity, we have no dielectrics or different material interfaces near to our qubits. As a result, we have the lowest charge noise of any solid state qubit. Then stability, our qubits are small, simple and pure. As a result, our cost-effective qubits have large energy separation and high stability. Efficiency, sub-nanometer engineering for nuclear spins creates efficient multi-qubit gates. This allows us to execute algorithms with unmatched performance. Accuracy, our qubits are naturally formed remarkably with 6 qubits per gate. We have the long coherence times necessary for complex computation. Purity, isotopically pure silicon isolates our qubits, protecting them from magnetic noise and source of decoherence in the environment. That's also something I mentioned before, right? Manufacturability, we control our own manufacturing and can develop a new chip in 1 to 2 weeks. As a result, we identify near-term opportunities at low cost. Scalability, the size of our qubits allows us to fit thousands on a chip. Our commercial scale quantum computer will fit on a fridge, a scalable, cost-efficient, effective solid-state platform. And then finally, speed, atomic precision engineering of our chip allows us to place our qubits and sensors close together. As a result, we have blindingly fast operations. And then again, we are at the end of the page. So I think that's probably everything about the chip. Here's something about the technology. So after me wild guessing a lot, let's see how much we can actually figure out about the true technology here. So phosphorus atoms precision placed in pure silicon, nature's perfect qubit. We've manufactured silence and stability, the most viable path to commercial scale quantum computing. SQC can see, build and control matter atom by atom, unrivaled manufacturing precision. And by the way, I mean, this is as you see also from the way that this is being communicated here, right? It's not just about building a quantum computer. It is, and I think that's always the case when you have very ambitious goals. In order to reach them, there are a lot of technological milestones that need to be reached. And this is true for every single quantum computing company. There are technical marvels happening along the way. And by the way, our silicon technology is very similar. It is kind of a result of the ambition to go to the moon and the requirement that, okay, you can't take tube transistors up to the sky because they will not survive on a rocket, or they're too bulky for a rocket. So somehow it needs to get smaller, and more or less that is the story about the silicon and how this came into place. And for example, these ultra-high vacuum chambers here, they are also more or less development from the mission to the moon, because until that time, when people were doing ultra-high vacuum physics, they would use glass for that. So we had all of these glass tubes. You still see them sometimes in these tube amplifiers, which are still using this glass tube type transistor settings. And until then, all the high vacuum physics was done with glass. But the problem is, if you send somebody to space, you need to have something that is vacuum tight, because space is vacuum and you want to keep the atmosphere inside. But you cannot build a rocket out of glass. So we needed to develop techniques to create a metal chamber, and that includes welding, for example, that is ultra-high vacuum proof. So the ultra-high vacuum welding, for example, and all of the sealing technology here was developed in the same approach and is now being used to build these quantum marvels here. And now talking about the quantum chips, right? We are trying to build quantum computers that can do crazy stuff if they are working. But on the way there, for example, here, we develop techniques, or not myself, but the team is developing a technique to precisely position an atom within a wafer. And I mean, that might not sound too exciting, but it actually is, because now you can create transistors based out of single atoms, which might become even interesting for the classical transistor industry today. And then, of course, it is also interesting for the quantum computers, right? But even if they might not be the first one to create the biggest quantum computer, they have created a technology that is probably extremely relevant also to other fields of development, maybe even to classical computing. Sorry for that excursion. Let's go back to the technology now. So precision atom qubit manufacturing, PAQ-Man. SQC is the only company worldwide that can manufacture quantum processors at atomic scale. This precision is foundational to achieving our ultra-high quality qubits. Then there's something about the control hardware that they make in-house on the on-premise computing. Then we see some chandeliers here, so some cryostat manufacturing at scale. And then we also see supply chain partners, so companies they work with. And there we see a lot of names that we also have seen previously in the Hidden Quantum Champions. Just to point out some of them. So we have, I think, Delft Circuits we already featured, Blue Force as a cryostat manufacturer, Oxford Instruments, who also make cryostats, but also some of the apparatus that is being used to produce those wafers. But there's also other ones, like for example MBE Komponenten in Germany, so for these molecular beam epitaxy chambers, and many, many more. Now, I think that was very interesting, even though we might have not, let's say, learned the absolute details of the technology. As per usual, let's quickly also use this to check out about the company itself. It says Pure Quantum Excellence here. Funded in 2017. I think we've seen these numbers before. Then we see some photos here. So what sets SQC apart? A material science approach to delivering the first commercial quantum computer. So the qubits, 14, 15 qubits, what you scale matters. Our quantum processors only contain two types of atoms, silicon 14 and phosphorus 15. This simplicity allows us to realize the highest fidelity algorithms of any platform, full stack. At the heart of SQC is our ability to control and deliver all through the quantum computing stack, from atomic scale processors manufacturing to integrate hardware, classical control systems, and software. And then we have here, let's say, I guess the founding brain behind the company, which is Professor Michelle Simmons. Michelle is an internationally acclaimed physicist and materials scientist renowned for creating the field of atomic electronics. For 25 plus years, she has pioneered the foundational technologies for building computing devices in silicon at atomic scale. She developed both the world's first single atom transistor and the first integrated circuit made with atomic precision. The SQC team is the unequivocal world leader in atomic scale manufacturing. These technologies are now being scaled to create useful products, including machine learning chips, analog simulators, quantum processors, and quantum computers. And then I guess here we see the whole team. So excellence in silicon. We have the world's leading experts and minds working on our technology and products. We see Professor Simmons as the CEO and founder, and Simon Sagers as chair. Then we see the team here, which, as mentioned already before, is very strong in engineering. So you have various different engineering people involved here. And then there's some milestones, I guess, that came along the journey mentioned down here. So it starts 1998 with Nature, first concept for an atom-based quantum computer in silicon. And then this is probably from that paper. 2003, first atomic precision placement of phosphorus atoms in silicon. 2004, complete chemical understanding of deterministic doping. 2004, high quality encapsulation of phosphorus atoms without segregation. And it goes on, right? I'm not going to go through every single one of them. But you see there's a lot of, let's say, steps that had happened before where we are now, and that kind of built on top of each other to create this great success of what SQC is doing right now and is capable of building. So let's see, it goes all the way to 2023, 2024, 2025. So SQC processors demonstrate world-leading algorithmic performance. And then 2025, SQC awarded place on DARPA Quantum Benchmarking Initiative program. Okay. And then again, the follow-up or the point here to keep in touch. I think that's everything for today. So that was, let's say, the story about silicon quantum computing. I hope you liked it. I hope you found it informative. If you like these types of videos, make sure to subscribe to this channel to not miss out on the next one. Also, make sure to stay hydrated, and I'm looking forward to see you in the next video. Until then, bye bye.